Okay, I just want to remind you guys what we were talking about. We've been talking about constitutive response of materials, and we started with elasticity and poroelasticity, viscoelasticity, and now we're talking about the inelastic response of materials. So, of course, when I say inelastic, I mean when we deform the material, we permanently change it. It will not return to its undeformed state. And we talked quite a bit about the Mohr-Coulomb. We looked at Mohr circles, and from that we talked about the Mohr-Coulomb. Oh, by the way, I know I'm behind on getting the videos put up. I think 2 or 3 videos. I have them all, and actually that's what I'm going to make sure I get done this afternoon while my daughter's in my office. So that'll be an easy thing to do. So I'll get those posted if you missed those. Anyway, so we talked about Mohr-Coulomb, which is a pressure-dependent material. If you remember, we had this kind of schematic in principal stress space of like a hexagon, something like this, that then had this conical-like shape in principal stress space which is centered on the line sigma 1 equals sigma 2 equals sigma 3. So because the pressure is essentially the sum of the principal stresses, this line represents the pressure dependence. So as we move up or down this line, the line sigma 1 equals sigma 2 equals sigma 3, we're changing the hydrostatic pressure on the sample and therefore changing its behavior, constitutive response. And so I just added another schematic here that shows you, this is from a different reference, but this shows you how extreme the pressure dependence on a rock can change its behavior. So this is a Carrara Marble, which look really nice on countertops, of course. You can see that at 0 confining pressure, so that's unconfined, then you basically have nearly elastic brittle behavior. So you have a response that's elastic, and if you were to stop deforming it anywhere along this curve, it would return to its undeformed shape. There's a small amount of inelasticity, but otherwise it fails catastrophically at very small strains. But if you just add a little bit of confining pressure, then the material has a lot of strain softening. So, of course, in the strain softening regime, this is, as we continue to strain the material, it requires less force to continue to strain it once we've passed this peak. So if we strain the material, once we pass that peak, we don't have to pull on it as hard, and we can continue to strain it. And this strain softening continues as we increase the confining pressure until eventually it turns over and becomes a strain hardening behavior. So up here, this is actually just the opposite behavior. This is if I pull on or strain the material, once I pass a certain point, now to strain it further, I have to pull on it even harder. So you get a complete reversal of the kind of softening to hardening regime just due to the confining pressure. And of course, these confining pressures are realistic at reservoir depths. I mean, this is what we see. So we need constitutive models that include pressure dependence, and we've talked about one, the Mohr-Coulomb. There are many others, some common ones, and so this is a view down the hydrostat, right? So this is a view looking down the line. This dot in the center is the line, sigma 1 equals sigma 2 equals sigma 3, right? And so here's our Mohr-Coulomb surface that we've already looked at. But there are many others that can describe the behavior of rock more accurately, and we'll look at a couple of those today, notably this Hope Brown, which looks similar. It's mostly hexagonal in shape, but what you can't see, it's hard to tell, is these sides are actually curved just a little bit. So what I traced in blue there, the sides between these points are just slightly curved, okay? If you look at the equations, you can tell that. And then there's some other ones that we won't look at in as much detail, but sometimes, of course, we want to use a constitutive model that describes the behavior of the rock to the most accuracy, right? But at the same time, when we actually solve these problems, we solve them in a computer. I mean, the form of the constitutive models are complex enough that even for like a Mohr-Coulomb, there's very few problems we can solve by hand, okay? So when we solve these by a computer, and when we do that, and this is an aside, you won't be tested on this, but just to let you know, when we do that, we use the idea of these yield surfaces are that the state of stress, and I think last time I had this little GUI, this little toy program that showed the Mohr circles and how if you rotated the stress around, the state of stress was always inside that larger circle, right? And it could never go outside it. And it's sort of, this is the idea that when we use these yield surface models, that the state of stress always has to be either inside that surface, in which case it's elastic, or it has to be identically on the surface, in which case it's inelastic or plastic. Okay? Now these, for very complex models, these surfaces can actually grow. So as you can, this is what happens in a strain hardening regime. So as in a strain hardening regime, if I have a stress strain roll that looks like this, once I pass this elastic point and I continue to move along this line, as I continue to move up this line, what's happening is these yield surfaces, these circles or hexagons that are actually growing, okay, permanently. They grow such that, because if I load up this line, so if I deform my material and I load up this line to this point and then I unload, and I think you guys saw this, it's going to unload elastically, right? It's going to unload elastically, such that if I go all the way down to where I have no force on my sample, this amount of strain will be permanent. It'll still be there, okay? Now if I load it up again, it's going to travel back up this line, and it won't reach inelastic behavior until it reaches this point again, and then it'll continue to load along that line, okay? So the idea here is that that yield surface grew. It grew from an original size, here, or parameterized by a value of like that. And as I continued to load it, it grew. Then when I unloaded it, it remained at this size, parameterized by that. And then as I reloaded it, it continued to grow, okay? So, again, this is just sort of an aside, but just to let you know. So when we solve these in a computer, we basically solve a optimization problem, essentially, a constraint optimization problem. This constraint is that the state of stress has to be inside or on that yield surface, okay? And what happens is, what you do is you basically, in the course of, in a computer, everything's discrete, right? So we take a discrete step in time or in load. We take a discrete step in time and in load, and that's, it's not like when we go to the lab and we turn on the machine and you get this continuous mechanical loading, right? In a computer, everything has to be finite, right? So we can take really tiny time steps and make it look smooth, but ultimately there's a discrete step there. Okay? And during that discrete step, I mean, it could be that one of those discrete steps is what takes you from elastic to plastic or elastic to inelastic. All right? And so what happens there, if you just evaluate your stress, like, you know, say you're in a state of stress according to the loading where you're inside the Drucker-Prager yield surface right here and everything's fine and dandy, then you take this discrete step and load and you find yourself, because initially you're inside, you're elastic, okay? You take this discrete step and load, the only thing you know how to do to evaluate the stress is to say it's elastic, and then you find yourself, because it's a discrete step, outside the yield surface. Okay, but this is in violation of that constraint. It's not allowed. You have to be inside the yield surface or on it. Okay, and so basically what we do is we solve an optimization problem, a constrained optimization problem, to get us back on the yield surface. Okay, and we enforce that with something mathematically that's essentially a Lagrange multiplier. So we get ourselves back on the yield surface. Okay, and so although this was a sort of a long-winded explanation to say, when we find ourselves outside the yield surface in this computational setting, we have to get ourselves back onto it. And one of the easiest ways to do that is to take what's called a normal return algorithm or a normal projection. So if we find ourselves out here, we project ourselves back onto the yield surface in a way using a vector that's normal to it. Okay? Well, what if I find myself, wait, what's the normal vector to, let me clear this off. What's the normal vector to this point on the Mohr-Coulomb yield surface? It's undefined. Right? There's no normal vector right at that sharp corner. So if we find ourselves in a very peculiar case where we need to return to the yield surface and the normal is very near that corner, this causes problems with our constrained optimization problem. It causes computational problems. Okay? And so what people have done is to propose yield surfaces that have smooth edges. Okay? And so some of these, like this circle inscribed in the center, or this outer circle, corresponds to a model called Drucker-Prager model. Okay. Now, it's not that, in this case, it's not that the Drucker-Prager model fits the data the best, okay, right? We really want to use constitutive models that best fit the data. But we also have to solve problems. And if the constitutive model that best fits the data gives us this odd scenario that it's also very hard to solve computationally, then we may approximate it some way. We say, okay, well, we know this doesn't fit the data perfectly, but we have another model that we can actually solve problems easier, so we're going to use that one. Right? So you really have to be engineers here in the sense that sometimes you have to allow for some approximation so that you can get things done. You can solve a problem computationally. Yeah.
Why can't you just find the point that's near,
You can, and there are certainly ways around it. I'm not saying that people don't use Mohr-Coulomb in computational code. They absolutely do all the time, and there's these techniques called pointer fans and all these other things. But usually it adds complexity to the computational model. So in computational modeling, and I know this isn't a course in computational modeling per se, but the reality is all real problems, real difficult problems, are solved in a computer and these days. And so in a computational setting, you're always trading off speed for stability for accuracy, right? There's no free lunch. There's never a scenario when you can have all three. you can increase the speed, increase the accuracy, and increase the stability or robustness of the numerical algorithm. It never happens. You're always trading off one for the other. So in this type of model, what you would do is you might trade accuracy for speed, because a return algorithm associated with these smooth yield surfaces are much faster. And so you're going to trade off a little bit of accuracy for speed. Now, if you really need the accuracy because you're solving a problem that's just really critically dependent, it's really sensitive to the material model, then in that case you have to give up the speed for the accuracy. So these are all decisions that we as numerical analysts or computational modelers are faced with all the time. Okay.